All right. Now, section 4. We end that chapter in the next. Okay, we end this chapter. Oh my goodness, lucky you. Next week is off, isn't it? So it won't. The chapter 3 will not be due next Wednesday. The what would that be? The 30th, which is spring break, but rather would be April the 6th. So chapter 3 is due on Wednesday, April 6th. We proceed. Chapter 4, exponential functions. An exponential function is the form a to the power x. Instead of x to some power a, it's a to the power x. A is the base, x is the exponent, therefore the name exponential. For example, y equals 2 to the x. And here's a table of values. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the second is 4, 2 to the 3 is 8, 2 to the negative 1 is a half, 2 to the negative 2 is a quarter, and 2 to the negative 3 is 1/8. Plotting these points, you get this graph here. Kind of a ski slope type. It starts very small and then winds up very big very quickly. And okay, the shape and direction of the graph depends on the base. 2 to the x is this graph here. 3 to the x starts smaller, grows quicker. 1.5 to the x begins bigger and grows slower. 1 to the x is constantly equal to 1, so it's a constant graph. 1/3 to the x graph is the same as a 3 to the x graph flipped left for right, because 1/a to the x is a to the negative x. 1/2 to the x is the same as 2 to the x graph flipped left for right. 2/3 to the x is the same as 1.5 to the x flipped left for right. They all go through the point 0 by 1 because a to the 0 is always equal to 1. I call this shape, by the way, the peacock's tail. If a is greater than 1, it starts small, ends big, like these. This is called an exponential explosion because they're in chemistry and physics. There are any number of physical systems exploding which have exponentials of this nature. Here, however, if a is between 0 and 1, it starts big and small, flipping this left for right. So this is known as exponential decay, and you guessed it, it's because it's the various forms of decay equations. Radioactive decay in particular are governed by exponential decays. Here's an exponential explosion. Compound interest. If we have a quantity of a fund with a constant interest rate, then if P is the initial amount of the account here, and A is the final value of the account here, and R is the annual interest rate here, and K is the number of compoundings per year. So quarterly compounding, K is 4, monthly compounding, K is 12, and so on. And T is the time in years, T, then A, the final value, equals P, the initial value, times 1 plus R over K to the KT. What K does is that it decreases the interest rate per period, but increases the number of periods in a given time. All right, so we have some examples. 5 to the x, graph y equals 5 to the x, that's an explosion. It starts small, goes to 0 by 1, and grows very quickly. Graph y equals 1/4 of the x, 1/4 is between 0 and 1, so it's a decay. It starts very big, goes to 0 by 1, and ends very small. Then they asked graph y equals 3 to the x minus 2. Well, 3 to the x starts small, ends big, and now we move it down 2. So instead of being asymptotic to the left to 0, it's asymptotic to y equals -2. Okay, so it starts at near -2. At 0, it's going to be 1 minus 2 is a -1, and then zip off to the sky like that. Y equals -2, the opposite of 2 to the x. Well, 2 to the x starts small, ends big. This flips the up or down like that. So it starts small negative and ends up big negative after going through 0 by -1. Here's a compound interest issue. It starts, principal starts out with $10,000 invested. Oh, boy, wouldn't I like that much. At an interest rate of 8%, quarterly compounding, K equals 4. How much does it grow to after 10 years? All right, here we go. The later amount A is P, principal times 1 plus R over K to the KT. It'll be $10,000 times 1 plus 0.08, that's 8%, over 4 to the power of 4 times 10. So 10,000 times 1.02 to the 40th. And okay, here's the point where you whip out your calculator, and aren't they convenient for that purpose? And you get 22,080.40. So it more than doubles, a little more than doubles in those 10 years. That's known as a doubling time. How much more interest would $10,000 earn at 5% compounded quarterly? At 5% interest, then at 5.5% interest, then at 5% interest. Okay, so we figure the later amount A at 5% interest and 5.5% interest. A equals P, that's $10,000 times 1 plus, here 0.05 over 4, here 0.055 over 4, both to the power of 4 times 5 years. And okay, after a bit of calculator, this is at 5%, it's $1,282.04. At 5.5% interest, it's $1,314.07. The difference is $32.03. So that's what that 0.5% interest is worth after 5 years. Okay, that's good. We have concluded our day's work.